Hey everybody, wanted to go over the Coulomb's law practice problems from the packet numbers 1 to 5. They're all about Coulomb's law, which is about electrostatic force between objects that have charge. So if they are missing electrons or they have extra electrons, then they have a charge. So there'll be force between objects with charge. Number one, two charged spheres are 0.45 meters from each other. One sphere is a charge of 1.5 times 10 to the negative 6 coulombs, and the second has a charge of 3.4 times 10 to the negative 6 coulombs. What is the force between them? First of all, those are, even though they have negative exponents, those two charges are both positive. So right away we know it's going to be a repulsive force or a pushing apart force. So really you just need to plug it into Coulomb's law. So Coulomb's law is force electrostatic is a constant K times the charge of each object divided by the distance between them squared. So in this problem we have two positively charged objects. They are some distance apart and they're going to have a repulsive force, and that's what we'd be solving for here. They are some distance apart. So in this problem, it is 0.45 meters apart, and one charge is 1.5 times 10 to the negative, I think it is 6, and the other one is 3.4 times 10 to the negative 6 coulombs. So it looks like each one of these is actually missing electrons. That's how you would get a positive charge. So we just have to plug things in. So this is a constant 9 times 10 to the 9th. You use that number every time, and then you put in the charges of each object and then the distance squared. This should look really familiar. This is an inverse square law, so gravity worked pretty much the same way. So let's figure it out. So we got force electrostatic is 9 times 10 to the 9th times 1.5 times 10 to the negative 6th times 3.4 times 10 to the negative 6th divided by 0.45 squared. So if you solve that down, you should get a small force, 0.23 newtons, and that would be the force between them. Electrostatic force is actually a really strong force. If you saw my round robin video where I took a balloon and I rubbed it on the fur, just moving some electrons around, I had a force stronger than gravity. So I had more force up than down, and that's why the balloon was stuck up to the fur. So it is a pretty strong force. The next parts are, if the distance in the problem above were to double, what would be the value? So it is an inverse square law. So the farther the distance, the weaker the force is going to be. So if we could just solve this with a relationship. So let's see again if the distance were to double. So if the distance were to double, here we go again with these relationship problems. So if the distance were to double, that distance, the effect of doubling that does get squared. So really you would be doing nothing to the top, or really multiplying it by 1. The bottom, the 2 would get squared, so you would have a fourth of what it was. So you could take this and divide by 4, which is, of course, 0.6 newtons then. So you're going to get weaker if you double the distance. The next part is if both charges were to double and the distance remained the same from number 2. So we'll keep that double distance in there, and then we can relate back to the original number again, the original force. So doubling the distance, and if both charges were to double, so we'd be putting a 2 and a 2. Q is the charge, so doubling both charges would have the effect of 4 times the effect on top, and then you would be doing the distance squared thing again, so 4 on the bottom. So doubling each charge, making them twice as strong makes it stronger, but at the same time, doubling the distance makes it weaker, and that's just going to cancel out. So we'd be back to the original force for the last part of number 1. Number 2, let's keep going. Let's see how long this will record without a break. Number 2, sugar poured from a box into a cereal bowl. This is kind of interesting. This is the type of stuff that I always felt I was weird because I would pay attention to the weirdest things. But I read this problem for the first time, and I'm like, oh yeah, sugar repels and attracts as you pour it from a sugar bowl. If you saw the round robin, I saw a lot of your great videos there. You would rub whatever object you could find with fur, and then with the salt, you could really see it attracting up and down. So if you're pouring it, the same thing would happen. It would be attractive and repulsive. Hi, Hunter. How are you? Yeah, let's see. Right, get out of here. Number 2, sugar is poured from the sugar bowl. As they rub together, there's going to be friction happening. There's going to be electrons moving. Things are going to get charges. So some of the sugar flies out. You can try this. Pour some sugar slowly from one container to another, and you'll see some like kind of bailing out. It's kind of neat. So 2 sugar grains acquire the same charge. So again, it's a negative exponent, negative 11 in number 2, 3 times 10 to the negative 11. But that's actually a positive charge. So again, it's going to be a repulsive force here. Positive and positives, like charges, repel. And they're at a separation distance. That is a really small number, 8 times 10 to the negative 5th. It's in meters, though. With what force will they repel each other? So you don't need a lot of force to propel a sugar granule. It's going to have very low mass, really low inertia. So a very small force could really have a dramatic acceleration on such a small mass. Anyway, let's solve the problem here. So you're just plugging it into the same equation. Force electrostatic. You're going to have that same number there, 9 times 10 to the 9th. It's a constant. It's always in the equation. It kind of corrects all the units out. And then we got the same charge there. So we got 3 times 10 to the negative 11. And we got 2 of those. You can either write it again or square it, either way. And then they are 8 times 10 to the negative 5th. Just careful how you put everything in your calculator there. Anyway, solve it out, and you should get a force electrostatic of 0.00127 newtons. Doesn't sound like a lot, but if we had the mass of a granule of sugar in kilograms, it would be a tiny number. F equals ma. You could still have a pretty good acceleration from such a light force. Let's try number 3. We got Bozo the clown. Bozo. All right. He's got 2 balloons. They rub against a circus elephant. I guess this was written quite in the past. Anyway, each balloon acquires a charge. Again, positive charges. They're going to repel each other, and they give us a distance. Pretty straightforward. Again, we're just solving for force each time so far. So really just plugging into what we call Coulomb's law. That's that equation. So let's just plug it in. Let's get the math done, and we'll move on to another one. So this is number 3. Force electrostatic, 9 times 10 to the 9th. This is a big constant. Comparing it to gravity's constant, that was a tiny, tiny, tiny number. And it kind of shows the relationship that this is a strong kind of force, and gravity was a weak kind of force. Anyway, let's keep going here. Am I still recording? Okay, good. Let's see, 9 times 10 to the 9th, we've got 2 times 10 to the negative 7, and they have the same charge again. We can square it or write it again, either way. And 0.5 squared for the distance, and you get a force of 0.00144 newtons, if I did my math correctly. Fact check me. Again, we're talking balloons, so a small force like that, the inertia of the mass of the balloon, we're not talking you don't need a big force to have a big repulsion, or a noticeable repulsion, I should say. Number 4. What's up at number 4? Perry uses hairspray. Each hair, before going to school, the spray spreads out before reaching the hair, partly because of forces. This is actually true. This is how a lot of aerosols actually behave. When you atomize or, create a mist, a lot of those interactions do create forces. What is neat is it's also, sometimes we do that intentionally. Right before we left school, I had heard they were disinfecting the rooms with a spray, and they would actually, apparently they were using electrostatic force so that the spray would actually be attracted to like every little crevice of the room and everything, it's actually kind of a neat idea. We also use that for there's an electro painting that we do where we charge, say, like the frame of something metal, and the paint then gets evenly coated to every little nook and cranny. Anyway, it reminds me of that. Number 4, sorry for the side trip there. So anyway, we just got to plug in. This time, careful, the distance is in centimeters, so we have to move our decimal over twice. What else? They're giving us the force this time, so we have to solve backward and just solve for the charge. Let's see. They're equally charged. So I remember from gravity, anytime we would ask you the charge and not tell you the other charge, we would say, and last time we would say m squared. Let me write the equation. So it is force electrostatic is K Q over D squared. Generally, so far we've been asking you force electrostatic from giving you the other information. So this time we want to know the charge. And the only time, what I was saying a moment ago, is the only time we would ask you a charge and not tell you the other charge so you could solve it mathematically is if they had the same charge. So we did something similar with gravity. So we'd say Q squared then. And then we're looking for Q. That would be the charge of each, a mist or droplet of hairspray. So we have everything but the Q this time. Remember, you always have K, 9 times 10 to the 9th. So let's just plug some numbers in and solve for this charge already. So it is 6 times 10 to the negative 9th is the force. 9 times 10 to the 9th is the K. That's always in there. We need the Q squared. That's what we're solving for. And then the distance converted over to meters. 0, 0, 0, 7. Is that correct? Yeah. And that is squared. Careful. So do your math, solve for Q. Remember, you got a square root at the end, and hopefully you should get 5.72 times 10 to the negative 13 coulombs. Cool. Last one. Jenna is dusting the house, raises a cloud of dust particles as she wipes across the table. Again, before we even get any further, there's a lot of cleaning products where there's a difference between some of them actually are just moving dust around, and some are actually creating charges and attracting or repulsing dust. I remember there's definitely some dusting sprays. I remember when I was a child that would repel dust. It was actually kind of neat. Anyway, all right, so Jen is dusting the house. It also reminds me of the old televisions used to get a charge on the screen. So the dust in your home would actually be a charge to the screen. It would be attracted. It doesn't happen with any of the modern televisions, but when I was a kid, you could run your finger across a screen and you'd almost hear static crackling, and you would always have dust on your finger. Oh, yeah, sorry. I guess I miss telling my stories, I guess. Number 5, so Jen is dusting the house. In this one, we're given the force. We always know K. We're given the charges, the same charge once again, and we're looking for the distance this time. Again, square rooting at the end, I imagine, because it is D squared in the equation. I hope I'm still recording. Looks like it. Number 5. So Jen is dusting. Oh, you know what? My names might be totally different. I just noticed that. I'm working off an older document. All right, that's going to look silly on the viewing side. Anyway, so I've got Jenna. I don't know who is dusting on your end. Sorry. She raises a cloud of dust. I know the numbers match. Let's see here. The force. So again, plugging into Fe is K Q over D squared. So we've got 2 times 10 to the negative 12th. That must be in newtons. And we've got 9 times 10 to the 9th. And we've got 4 times 10 to the negative 14th. That is squared. We don't know D. Careful, D is squared in the equation. It is an inverse square law. Anyway, solve for distance, and again, square root at the end, and you get a small distance. It is in meters, so it is not tiny. 0.027 meters. Boom. All right. Hope that helped. We should be able to solve force problems kind of backward, forward, solve for the force, solve for the charge, solve for the distance, and maybe do a relationship type problem. All right. Kind of miss you guys. See you later.